guys, welcome to 3.3, Making Sense of Your Data. This is our last little video chat here before the end of the school year. It's been a good one. I'll miss you guys. I'm sure you're very excited to move forward, graduation in college. So let's go ahead and get started. Let's make sense of your data. So now that you have it, you've created two visual representations of each population's information. You've found your curve of best fit, and you've found the derivative or gradient function of your curve. So what are you going to do with it? How are you going to make it meaningful? Well, the first step might be comparing your graphs. Here, I took the New York State data from our last lesson, and I did the same analysis with data from the state of Virginia. Now you can see here there's a very distinct difference in not only the shape of the data, but the number. You can see here that our scale for new cases in New York goes all the way up to 12,500, whereas in Virginia, our scale goes up to about 600. Looking at our scatter plot, you can see a lot more variation in later days in Virginia. So looking at those, you need to ask, what patterns do we see for our focus population, which here is New York, that are not there for our comparison population, Virginia, and vice versa? What could give those differences meaning? Well, at what day after the first case in the state did New York order a stay-at-home order? What about Virginia? If it doesn't really have anything to do with day, take a look at how many cases there were in the state when the order was given. You can also look at proportions versus counts. The United States Census Bureau estimates New York State's population at 19,453,561, while Virginia's is 8,535,519. We can also look at the rates of change for disease spread at intervals. I randomly chose 10, 20, and 30 days. You can choose whichever interval you like. Now, using the information on New York that I got, where we found last class that the logistic function is our curve of best fit, we got our A, B, and C and plugged it in. And we saw that it fit our curve really well with an R squared of 0.94. Then you found your derivative or gradient function, and we've plugged in the values of A, B, and C to get the function that we can then evaluate. So evaluating at 10 days, 20 days, and 30 days. When I plugged 10 into the original function, I got 447. And when I plugged 10 into the derivative or gradient function, I got 139. This means that 10 days after the initial case in New York, there were 447 new cases, or there should have been according to our curve. And the number of new cases was increasing at a rate of 139 new cases per day. Now, that doesn't mean that there would be 139 new cases. There would be 139 more new cases than there was the day before. At 20, we had 5,260 as our predicted number of new cases, and the number of new cases was increasing at a rate of 735 per day. At 30 days, we were looking at a predicted amount of 8,942 new cases, and the number of new cases was increasing at a rate of 81 per day. So you can see that your rate of change actually decreased at day 30. So you can now compare them. And the first thing you can look at is, does your predicted number of cases match your actual data? Here, they're a little different. By how much? Well, that difference is going to be explained by the fact that there's still 6% of variation in Y that is not explained by the change in X via our curve of best fit equation. What does that mean about the validity of your study? Is your study still valid if you have error? Yes. If you want to find the sum of your squared errors, like we did in our regression unit, you absolutely can. Find your predicted value and then subtract that from the actual value. Take a look at your error. Comparing that to Virginia, Virginia also best fit a logistic distribution. However, R squared was only 0.8751, which means that it didn't fit this curve as well as it fit the New York curve. And you can see that here. Looking here, there's a lot of variation in Virginia in the last 10 days of our tracking here. Then you can look when we started plugging in those same day intervals to both the original function and the derivative or gradient function. At 10 days, we predict Virginia to have 9 cases. And actually, that number is increasing at a rate of 2 more per day. And that's at 10 days. At 20 days, we have 90 cases. And the number of new cases per day is increasing at a rate of 17 more new cases per day. At 30 days, 324. And we're still increasing. Remember, New York, the amount decreased. But in Virginia, we are still increasing. So we can compare, kind of like I just did, those predicted numbers at your set intervals for your focus population and then your comparison population. What similarities are there? What differences are there? And why do you think these are happening? So here's where you can look at policies that the different governments have put in place to help flatten the curve. Why is New York's rate decreasing, but Virginia's is increasing? Is it because New York has already hit its peak and it was way up here, and now it'll start descending while Virginia is slowly still climbing towards its peak? Why would that be important? How could the number of people sick all at one time affect things like hospital beds, nurses, doctors, PPE availability? That's all for you to think about as you go to write your report. But hopefully, this has helped you get an idea of how you can start making sense of your data. All right, guys, it's been fun. Have a good one.